While today's video will go over section 2.2 notes, you should also take out a piece of scrapbook paper to answer a few questions before we get there. Once you have that piece of paper out, go ahead and pause this video to answer this question. What is the rate of change in the following table? Once you've got an answer, go ahead and unpause to check your work. As we said in section 2.1, we can find change by taking the difference between two numbers. So to find the change in pounds, we'd take 7 minus 4 to get a change of 3 pounds, and the change in cost by taking $13.93 minus $3.96 to get a total change of $5.97. But as we said before, a rate of change is simply the change in the output divided by the change in the input. So our change in our output is $5.97 divided by 3 pounds. I could also write this as a unit rate by taking $5.97 divided by 3, telling me that my cost is $1.99 per pound. So this is a rate of change that you actually might see at a place like a grocery store, say if you are buying apples and they cost $1.99 per pound. You could use this along with how many pounds of apples you're buying to determine your total cost. For my next few questions, you are going to be identifying a pattern. So our pattern will start with this figure that we will state as case 1. How many squares do you see? Next, we will continue the pattern by looking at case 2. Once again, how many squares do you see? And then what about case 3? How many squares are there? On your scrap piece of paper, I want you to draw what case 4 would look like. Go ahead and pause the video to take the moment to do that. Hopefully you recognize that case 4 would have 4 squares here in the corner, and then 4 above, and 4 to the right. So there would be a total of 12 squares in case 4. Next, go ahead and pause the video and think about what would case 100 look like. How many squares in this case would there be? So to continue this pattern, once again, we would still have the 4 squares in the corner for case 100. But now we would have 100 additional squares above and 100 additional squares to the right. So to determine how many squares there are, I'd have 2 sets of 100 and then add the original 4 to that. So total, there would be 204 squares. So from here, we want to go back and think about rate of change. What is the rate of change from case to case in this pattern? Well, hopefully you recognized in the pattern that you were adding 1 from each previous case. So, adding 1 onto both sides. So that means that our rate of change was actually 2 squares per case. Now, this is going to be important in just a moment. So our next question, we've figured out the number of squares for all these different cases, but can we generalize this idea? And what I mean by that is how many squares are there in case X. So can you come up with an expression that involves the variable X that would tell us how many squares there are? Well, to figure this out, it actually goes back to case 0, right? Because we know case 0 started with these 4 original squares. And from there, we just added on to every single time. But what happens is we can actually take the case number and multiply it by 2 and then add the original 4 to tell us how many squares there are. And we can see this is apparent in every single one of these cases. So for case 1, 2 times 1 plus 4 gives me the 6 total squares. Case 2, 2 times 2 plus 4 gives me 8 total squares. For case 3, I take 2 times 3 plus 4 to get the 10 squares, and then case 4, 2 times 4 plus 4 to get the 12 squares. So this expression generalizes this pattern for us. And we can even turn it into a function by setting it equal to another variable, in this case y. So the function y equals 2x plus 4 is defined by the fact that the starting number is 4 and the rate of change is 2. So this is a very important idea that leads us into today's lesson. So at this point, go ahead and take out your notes for section 2.2. So linear functions are formed by straight lines. So if we were to look at a graph of our original pattern from the one we just looked at, y equals 2x plus 4, then I'd have a starting point at 4, and my line would increase by 2 squares per case. So really that should be a straight line. So just pretend that it is. However, we can always represent the equation of a linear function using this format that we call slope-intercept form. So notice we still have our x variable and our y variable, which represents our inputs and outputs, but then our line is defined by the values of m and b. So m represents the slope of the line. As we said in section 2.1, this is the same idea as the rate of change. And we defined rate of change as the change in our y value, or the change in the output, divided by the change in our x value, or the change in the input. Now, visually, what this looks like, or what we can compare it to, is the idea of rise over run. So again, looking at this example, we said our rate of change is 2 over 1. So from the starting point, we would rise 2 units that represented adding 2 squares, and then run 1 unit, which represented the very next case number. So we say rise because the y-axis is vertical, so we're moving up or down, and run represents the x variable, which is horizontal, so we moved left and right. We also have a formula to calculate rate of change, or slope, which you actually used in the warm-up question from today, comparing the cost to the number of pounds. So what this looks like is y2 minus y1 So that represents the change in your outputs divided by x2 minus x1. And that represents the change in your inputs. So we're just taking the difference between the two. So our rate of change, aka our slope, is one thing that defines the line itself. The second thing is the y-intercept, and that is denoted by the letter B. So we refer to this as our starting or our initial amount. Just like in the previous pattern, case 0 had a starting number of squares of 4. The y-intercept is also the point that's on the y-axis. So that is the mathematical definition, that it's the point that intersects the y-axis. Because of this, that y-intercept always has an x-coordinate of 0. So then the ordered pair would always be 0, comma, b. So whatever the value of b is your y-intercept. Next, we're going to take a look at a few examples of graphing a linear function given the equation. So what we're really doing is identifying the two pieces that define the line. As we said above, that is their slope and their y-intercept. So in this first example, the slope is 2. Now, if you want to think about slope always as a rate of change, then we would just say the slope is 2 divided by 1. Then our y-intercept is -4. So you can see that on the graph down here, and then the rate of change of 2 over 1. We can also see this in the table by showing that the y values are changing by 2 units or increasing by 2 every time the x value increases by 1. So once again, I can show this from point to point. So increased by 2, increased by 1. And that follows the idea of our rate of change. In the second example, y equals -5/4 x plus 4, our b value or starting amount is 4, and our slope is -5/4. So notice a common theme as well. We always multiply our slope by the value of x. Now, to graph this, I need to plot a point at 4, aka my starting point. And from here, the slope or the rate of change tells me how to move to the next point. So my change in y is the top number, which is -5, and my change in x is the bottom number, which is 4. So to change by -5 in y, I have to go down 5 units. And to change by +4 in x, I need to move to the right 4 units. So my next point would be right here. And I only actually need 2 points to create a straight line. Now, we've always talked about writing a rate as a unit rate normally. And what that would look like here is -0.8 divided by 1. That would be the unit rate. But it's a little bit more difficult to move in any one direction when we're not dealing with whole numbers. And that's why in this case, we stick with this fraction of -5/4. In the next example, this is actually a very special case. So this equation or this function does not have a y-intercept itself. And in fact, the slope is undefined. So you might be wondering, okay, well then how do we graph this? So in fact, the graph itself means that all of the points will always have an x-coordinate of 4. So here's a point with an x-coordinate of 4. Here's another point with an x-coordinate of 4, and another, and another. But notice if I continuously created points with an x-coordinate of 4, I'm just going to create this vertical line. So from here you can see this line never crosses the y-axis, so there is no starting amount. And since the slope is straight up and down, we would say this is undefined. Because what's happening, so say I want to go from this point to this point, my change in y would be a value of 3, but my change in x would not be anything at all, it would be 0. And if you try to divide anything by 0, you're going to get an error. And that's why we say that the slope here is undefined. Looking at the bottom center graph next, we might think that this equation looks different because we're not adding or subtracting a number at the end to tell us where our starting amount is. So if you think about it, since we're not adding or subtracting anything, that's the same as adding or subtracting a value of 0. So this means our starting amount itself is just 0, and that would be the point 0, 0. But then our slope or rate of change is 1/2. So from this point, that means my change in y is 1. So I'm going up 1 unit. And then the change in x is 2, so I'm moving to the right 2 units. I could do that again if I wanted to get another point on my line. I could even go backwards. I could go down 1 unit and to the left 2 units. And in the end, I'm still going to create my linear function. And in the final example on this page, this equation is actually also written a little differently. So our b value, aka our starting amount, has actually been written first. So that means b equals 3. If you think about it, another way to write this equation would be y equals negative x plus 3. And there it's a little bit more clear to see that's where our b value comes from. We also have to recognize that this negative x really means negative 1x. And therefore, our slope or our rate of change is negative 1. So what that means, we start at a point of 3. And our rise is negative 1. So I'm going down 1 unit, but then over 1 unit. So my next point would be here. So down 1, over 1. And that's going to allow me to create my straight line going through all of those points. Now notice, since our slope is negative, we're actually decreasing, and that's why the line is trending downwards, as opposed to the previous graph. Since our slope was positive, our line was trending upwards because it was increasing from point to point. Now we can actually reverse gears, and instead of being given the equation to draw the graph, we can take a graph and write the equation of a line by, again, identifying what are the slope and what is the y-intercept. So in this first example, notice our y-intercept has a value of negative 1, and our slope has a rise of negative 2, a run of 5, so we'd say negative 2/5. All right, if we go back to slope-intercept form, notice we're always multiplying our slope or rate of change by x and then adding the value of b. So the equation of this line would be y equals negative 2/5 times x We could say either plus -1 or just simply write it as -1. Both mean the same thing. In the second graph, this is another example of a special case. So if we count, the b value is 5. But now if we look at our rise and our run to get from this point to this point, I have a run of 4, but now my rise is 0. But if you think about it, 0 divided by 4 is still just 0. So our slope in this case is 0, meaning we could write the equation as y equals 0, x plus 5, but that simplifies to the equation y equals 5. So if you recall from the previous page, a graph that looks like this will be in the form of x equals a number, and then a graph that has a horizontal line will be in the form of y equals a number. So once again, in the case of this graph, we've already stated that there is no y-intercept because it never crosses the y-axis, and that the slope is undefined. But the equation itself is simply the same as the x-intercept. So in this case, our x-intercept is right here since it's crossing the x-axis, and notice that is at -4. And all of the points on this line have an x-coordinate of -4, and that is why the equation is simply just x equals -4. To finish up, we have to recognize that not every equation will be written in the form that we like it to be. So if it's not written in slope-intercept form, can we still determine the slope and the y-intercept of the line? So my first question is, looking at 2y equals 6x minus 8, why is this equation not in slope-intercept form? So pause the video to think about that for a moment. So this equation is not in slope-intercept form because it is not solved for y. So any linear function written in slope-intercept form starts with y equals. But just because it's not solved for y does not mean in this case that we're not looking at a linear function. But we can determine the slope and the y-intercept by just putting it into the form that we want it. So in this case, to solve for y, we would divide both sides by 2. And then simplify. So 2y divided by 2 simplifies to y. 6x minus 8 simplifies to 3x minus 4. So we've now put this in slope-intercept form, which allows us to identify the slope. Once again, slope is just our rate of change, and the y-intercept is -4. And then from there, we can graph it to create our line. Notice the second equation is even crazier. Both x and y are on the same side. Now, we'll learn a little bit later that this is actually called standard form, but we still want to think about what the equation would look like in slope-intercept form. So once again, we have to solve for the variable y. To do that, we'd start by subtracting 4x from both sides. That simplifies to -3y equals 9 minus 4x. And since these are not like terms, I can't combine them. I keep it as is. And then I divide everything by -3. So simplifying, that becomes y equals negative 3 plus 4/3 x. So now I can recognize that my slope is 4/3. My y-intercept is negative 3, which then allows me to graph the line. So negative 3, up 4 units over 3 units to get my next point. And from there, I have my line. Lastly, we are going to summarize the notes that we took today. So before you listen to the answers of all of these, I want you to take a moment to see if you can answer them yourself by taking a look back at the notes. Go ahead and pause the video, and then when you are finished, hit play. So what letter is used to represent slope? That is M. Remember that we also call the slope the rate of change. The letter used to represent the y-intercept is B. What is always true about a y-intercept? So here we might say that because it's on the y-axis, it always has an x-coordinate of 0. So we might say that because it's a y-intercept is on the y-axis, it always has an x-coordinate of 0. Next question, why is slope a ratio/fraction? Well, this goes back to the fact that slope is the same as rate of change. So we describe it as a rate that compares the change in y values to the change in x values. Now, we have seen slopes that aren't technically written as fractions. So maybe we have a slope of 5. But remember, that can be written as a fraction because it's equivalent to 5 divided by 1. So we'd still be stating that 5 is the change in y value compared to 1 is the change in x values. What does it mean if slope/rate of change is negative? What does the line look like? So this goes back to the fact that we're comparing the change in y to the change in x. So what this really means, as the x value increases, the y value decreases. So the line itself goes down from left to right. So again, a negative rate of change means that overall you are decreasing. And lastly, to find the slope of the line between the following 2 points, we could use the formula that we wrote down on the very first page. So we could identify this first point as x1 and y1, and then the second point is x2 and y2. So to find the slope, we'd take the change in the y values, so 6 minus 1, and then the change in the x values, so 2 minus negative 1. So the change between 1 and 6 is 5, and the change between negative 1 and 2 is actually 3 units, right? Because there's 3 units in between those two numbers, and 2 minus negative 1 is the same as 2 plus 1. So mathematically, we can see that that's a difference of 3. Therefore, our slope between those 2 points is 5/3. From here, you are only completing the practice questions that are circled. And remember that this video will be also posted to my YouTube page. That way you can reference it whenever you need.